In this video, we'll introduce the Rossmann-Chance applet to show how to create a simulated distribution of sample statistics using a computer applet. So recall, we can use a computer simulation to create a simulated distribution of sample statistics. Why would we do that? Because we want to see the range, the variety of expected sample statistics if we have a given population parameter and a given sample size. This is the link that can access the list of Rossmann-Chance applets. We'll go to that in a moment, but if you want to type that in your own computer to follow along, that would be the link to go to. So for this example, as we go through it, we're going to have the following scenario. Suppose I have a fair die. A fair die means it would roll any of the 6 faces of the die in equal proportion in the long run. So let's go ahead and just focus on the die rolling the face that has a 5 on it. So if it was a fair die, it would roll 5s a sixth of the time in the long run. If you look at the number 1/6 as a decimal, that would be the number 0.167. So as a percentage, that's 16.7% of the time that it would roll 5s. This is telling us that the long run proportion of times is the number 0.167. I'm just rounding that, and we'll stick with that rounded value. This is the population parameter. All rolls of the die would be the proportion 1/6 of the time would be 5s. So our question is this: if I roll this die 60 times in a row, what percentage of 5s would be usual, expected, versus what percentage of 5s would be unusual, unexpected? What we're asking about here is what we should expect if we take a sample of rolls. And in this case, we're saying the sample size is 60 rolls. And we're asking, when we do the 60 rolls and we get a sample statistic p-hat, what would be usual expected p-hats to get versus what would be unusual unexpected p-hats to get? How do we figure that out? Well, we could create a simulated distribution of sample statistics to show us the statistics that we expect to see when rolling a die 60 times. We will end up with that normal shaped distribution of sample statistics. In this case, it would be a distribution of p-hats. These are the p-hats you would simulate, the p-hats you would be expected to get when rolling the die 60 times in a row. It would be centered at about pi equals 0.167. Remember that your distribution of sample statistics will be centered at the population parameter. About half the time we'd expect to get slightly more than a sixth of them being rolling 5s, and we'd expect about half the time when we roll it 60 times we'd get a little less than a sixth of them being rolling 5s. Lastly, we could use that 2 standard deviation rule to understand, well, which of these are unexpected statistics and which of these are expected. So we would find the standard deviation. We'd go out 2 standard deviations to find out these cutoff values. We'd say these statistics up here are unusually high, so it'd be unusual to get this many 5s out of 60 rolls, and these down here would be unusually low. So if you rolled it 60 times, it would be unusual to get this few 5s when you roll it. And then we'd have an understanding of what percentage of the time we should expect to roll a 5 when we roll it 60 times. So how do you do it? Well, we're going to go to that link, the Rossmann-Chance applets link, and I'll open that now. Here's what it looks like. We are talking about proportions. We are asking about pi equals 1/6, that's the population proportion, and we're interested in understanding the distribution of sample statistics, the distribution of p-hats we expect to get, knowing that value of pi. So we are going to use this one proportion inference applet right here. We click into the one proportion inference applet. So you go to the one proportion inference applet. Make sure you always hide the coins first. So that's up in the top right corner. Click hide coins so that when you do your simulation, you don't get a bunch of coins or spinners. All right, And now this little description over here on the left in our file explains to us the three things that you need to fill in. Probability of heads. This is where you need to write the population proportion pi. So we said our distribution has a population proportion of 0.167. You do have to enter it as a decimal. You can't write 1/6 in there. So it's the value you're assuming. Now notice the default in this applet is that it says probability of heads. But once you press enter on this right here, it will change it to now say probability of success pi. Unfortunately, that should be the default in this applet, but it's not. It can be a little confusing the first times you guys start using this. But always, that first box is where you put the value of the population parameter pi. Next, in the number of tosses box, that is where you put the sample size. So again, in the applet, once you entered something other than 0.5 in that first box, it now actually says sample size n. So it's a lot easier for you to fill that in and understand that you're putting in there is sample size 60. When you first access this applet, though, it actually says number of tosses until you change that very first box to something other than 0.5. And lastly, it asks for the number of samples. Number of samples, number of repetitions, is how many dots you want in your distribution. It is how many times you want to take a sample of 60 from the population. So, for example, if I put 1 in here and I hit draw samples, the computer will simulate pulling a sample of size 60 and it will give me the result. This dot right here is the computer simulating rolling a fair die 60 times, and it says that I got 9 times that it rolled a 5 out of 60 rolls. If I hit draw samples again, it will draw 1 more, and now this time I got a dot here at 8. So it rolled the die another time, 60 times in a row, and this time it got 8 5s out of the 60 rolls. I hit it again. This time it got 5 5s out of 60 rolls. Now it got 11 5s out of 60 rolls. So I can just keep hitting that and it keeps adding dots over and over. Each one of the dots is saying, well, if you have this fair die, you roll it 60 times. Here is how many 5s it rolled in the 60 total rolls. Now, another way to do this, let me just reset that. Another way to do this is to actually just hit number of samples is about 100, and it will just automatically give you 100 dots. So each dot is the computer doing 60 rolls of a fair die, and it's telling you how many successes, how many times it rolled 5 out of 60 attempts. There is also a button down here for switching between number of successes and proportion of successes. Notice, number of successes will tell you exactly how many times out of 60 it rolled the 5. Proportion of successes will give that to you as a decimal proportion. So for example, these 2 dots up here on the right above the number 15 tell us that twice the computer rolled the die 60 times and the result was rolling a 5 15 times out of 60. 15 times out of 60 means 25% 5s. 25% of the time it rolled a 5. So if I switch to proportion, this 15 right here will now be 0.25. 25% 5s when you roll the die. So they are the same distribution, they are just labeled differently. It is very important that you pay attention to that and understand which one you're looking at when you're writing your sentences to interpret values. The last thing that you need to be aware of when you're creating your simulated distribution of sample statistics is this button here for summary stats. If you click it, up in the top left-hand corner, it will tell you the mean of your simulated distribution as well as the standard deviation of your simulated distribution. Remember, this is a simulation. If you start over and create a different simulated distribution, or your neighbor next to you on a different computer does the same values entered and creates a simulated distribution, you will all have a slightly different simulated distribution. right? It's the computer saying, I rolled the die 60 times, here's how many fives I got. I rolled the die 60 times again, here's how many fives I got, over and over and over. So if you repeat this, you're going to get slightly different dots in this distribution, and your neighbor will get slightly different dots. However, they will all be extremely similar. The mean of each of them will all be very near the population mean of 0.167. See, this one had a mean of the distribution of 0.17. You might have a value slightly less than 0.167 when you do the simulation, but they will be very similar. Once you have that distribution of sample statistics from your simulator, you can then use it to make conclusions.